Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Marina Kounkel with us today. Hi, Marina.
Hello. Hello. Thank you for inviting me again.
Well, thank you for agreeing to talk about your super lovely article. I think it's a fantastic one, complete with an interactive figure that we will see. So it's very cool. It's very cool. Marina, where are you at these days?
So I am currently at Vanderbilt University in Nashville.
Okay. Okay.
Yep. Currently a postdoc.
Okay. Awesome. Very cool. Very cool. So summer's in full bloom in Tennessee area.
Yes, it has been exceedingly hot in this area as of late.
Yeah. Yeah. Do you get I think they're a little too north. You don't get like tornadoes or something there. I think it's a little too high for that.
We've had a couple of warnings.
Okay. Okay. Good. And I'm in Phoenix on this August 17th of 2022, and we are definitely in full summer bloom, which means we get a lot of rain, thunderstorms. This is the wet season in Phoenix, so it's very good. It's good for my grapes. So my grapes love it. It's very cool. And Marina, what do you like to do for research?
So I am interested in dynamics of young stars and dynamics across all scales, from scales of individual binary systems to individual clusters to their motion within the galaxy. Lately, so in the paper that we'll be discussing today, we were looking at the dynamics of young stars in Perseus.
Very nice. Very nice. Great research topic. And that is going to bring us to this awesome HA article. It's open access, people. You can go get it for free. Go grab it. The Dynamical Star Forming History of Per-OB2. And Marina, take us away.
Yes. So this is a work that we've done with an undergraduate student, Ting Yang,
Nice.
for the summer. And so we were finally able to write it up. So Perseus is one of the nearby star-forming regions. It's located only around 300 parsecs away, and it has typical ages of just a few million years. And for the most part, when people talk about Per-OB2, chances are, more often than not, they are referring to two specific clusters within it, NGC 1333 and IC 348.
Okay.
And if you scroll down to the figure 1,
let's take a look at figure 1.
Yeah.
We got data, we got the ages, figure 1. Yep, let's get the image going. All right, here we go.
So this is how it looks like in the plane of the sky. So you have IC348, kind of the massive cluster in the center. And you have NGC 1333 that is located just south of it. And the reason why it's usually these two clusters that people normally think about is because they are the clusters still associated with molecular gas.
Okay.
They'll have a large disk fraction of interplanetary disks. So people have been able to identify them in the Spitzer surveys of the regions. So there have been quite large-scale maps of these two clusters. Yeah. But most of the other stars in Per-OB2, so all of the stuff located to the north of it, they are no longer associated with molecular gas. Okay. And so now people have known that there is this region over here, that there are still young stars in this region. Prior to Gaia, it has been kind of difficult to identify the sources there. So people haven't really looked all that much. So people have looked at the OB stars, hence why it's called an OB associations. But the lower mass stars have historically been difficult to identify as young and to separate them from everything else. But now with Gaia, we have a variety of different means to search for these stars, because when stars are forming, they're forming from the same molecular cloud. The cloud has a particular velocity. Stars inherit the same velocity as the cloud. And so by looking at the overdensity in the proper motion space, it's possible to select them out quite nicely.
Okay, cool.
And so we've performed clustering of the Gaia data to identify quite a few subclusters in this regions. So there are various groups that have been named after various Perseus children.
Yeah.
Mythology. We can't claim credit for it. There was another paper that decided on this naming convention first, but we did kind of fill up some of these groups a bit more.
Right.
And California is located to, it's associated with the California cloud. It's not traditionally associated with per OB2, but it's also, it's slightly further away, around 500 parsecs, but it's also an interesting in the vicinity.
Comes in. Okay.
And so these stars, they're still pre-main sequence. That is to say, they are located very much very high above the main sequence. And with clustering, you can't necessarily recover all of the young stars because some of them are starting to dissipate.
Right.
Some you do have clusters, but you do have a slightly more distributed populations, and sometimes it may be difficult to get the substructure while getting the full structure at the same time. So there has been another study of pre-main sequence stars just across the entire sky, and so you see all the various black dots. Those are all of the pre-main sequence stars that are known in the region. So you see that we may be still missing just a little bit towards the top left of per OB2.
Yeah.
But for the most part, we are able to recover its extent.
Very good. Very good.
And all of these sources are color-coded by the ages of the stars within them. And if we scroll to the HR diagrams.
Sure. Let's take a look how those ages were got. HR diagrams. Nice table there. All the groups. LB. Okay. A little closer there. HRs. Here we go. We'll do a global and I'll zoom in as you want.
Yep. No, the global is fine. So again, these stars are the pre-main sequence. The main sequence you can see via a gray line. You can also see where the binary sequence of the main sequence is with a dashed line. And you see they're still located very high up above the main sequence. So there's not really much of a contamination outside of California cloud, where the clustering did produce a bit of contamination because it is a bit further away. But for the most part, the selection is pretty clean.
Very nice. Here we go in here. Electron.
Yep.
Altheus. Cinerus, if that's how you say it.
Yeah.
Very good. Okay. Got it.
And there are various models that try to predict how the photometry of the star should evolve as a function of age. None of those models are perfect. This particular isochron model MIST seemed to be working fairly well, but there are always going to be some systematic deviations. And, of course, how you treat extinction does affect the type of ages that you're getting. But for the most part, the ages of the stars here span a few million years, and they're not really that different from one another.
Right. Let me ask one question. I'll believe that MIST will give you the single star tracks. How do you estimate the binaries from that? The dash.
So this is just basically take the photometry of two equal mass stars and just offset
Yeah. I'm good. Yes.
Around half a magnitude, give or take.
I'm with you. Good.
And yeah, so the two oldest groups, Cinerus and Alcaeus, they have an age of around 7 million years or so.
Thereabouts, yes. Very good. Nice.
And so this region is interesting because, I mean, in the plane of sky, it looks like a mess. And you've seen it before that you have clusters, but they aren't oriented in any particular manner like you would expect with the clouds. They don't form a filament necessarily.
Okay.
But we can take a look at how everything is structured in three-dimensional space.
Very nice.
And here we can switch over to the interactive panel.
Let's go to the interactive panel, figure 6. So this is the figure associated with it, and we're going to shift over to the interactive panel here. One sec. And here we go.
And let's recenter it. So let's plot it along the x-axis. Yeah.
There we go.
So here, let's zoom in a bit.
Okay.
If you just use a scroll wheel, you
Got
can
it.
zoom in.
That? No. We'll just zoom.
Sure.
Boom, boom, boom. I'm not getting a zoom. Oh well.
You zoom and you draw on top of the figure to zoom in a particular box.
Got it. Ah, very good. I'm with you.
Yep. So here we can hover over various dots to get information on what regions.
Ooh, very nice.
You can see that there is chaos. There is beneath it. Just beneath it, there is Otoshte and NGC 1333. And
Yes.
all of the other groups, IC 348 is kind of in the middle, and some of the other older groups are to the side. And looking here, you can kind of see that various groups trace back to a similar point.
Yes. Let me zoom in a little bit. Yep. This grouping. Yes.
But the other three groups, they don't, well, we'll ignore California for now and Taurus for now. But the other three groups that are near the black line, they don't trace back from the same point.
Right. And what is the dark line here?
So the dark line is the trace of the molecular cloud. So previously, I've mentioned that IC 348 and NGC 1333, they lie on top of the cloud, and you can get the morphology of the cloud using extinction.
Very cool.
By looking at all of the field stars, you can see how the extinction changes, and you can get its overall trajectory. And the surprising thing that happened in the recent paper is that they said that, all right, even so NGC 1333 is associated with a cloud, IC 348 may not actually be. So they are projected along the same line of sight. And actually you click on the plane of the sky. That's helpful. Yeah, so right now this is how everything looks like if we were to look at it on the plane of the sky, similar to the figure that we were showing before.
Oh, I see.
So everything is kind of projected on the same line of sight, but because of the distances, IC 348 cluster isn't actually associated with a cloud. It's sitting something like 10 or 20 parsecs away from it.
Okay.
And that was kind of a surprise because, I mean, the cloud itself is, I mean, it has formed a star. Why wouldn't this cluster be associated with a cloud? Is this an error in measurements? Well, the measurements with Gaia that we have are quite precise. So that's kind of confusing. And looking at the proper motions and just kinematics of the stars in general, even so NGC 1333 and IC 348, I mean, they are projected along the same line of sight, but they have two very distinct set of kinematics. That IC 348 is tracing back to the same point together with all the other groups that are sitting behind the cloud. But IC 348, NGC 1333 rather, they are moving in a completely different direction.
Right. Yes. Okay.
And that's not what you expect, because again, when stars form from the molecular gas, they should inherit the velocities of that gas. The cloud itself shouldn't have that larger velocity gradient. So what is happening there?
Yeah.
There have to have been two different populations there.
Right.
Except Perseus is kind of in an interesting place. It's located pretty low down from the galactic plane. So you can see where the Z of 0 is. That is the galactic plane.
Yes.
This is located pretty far down. And in the solar neighborhood, we do have a thing called the Gould's belt. So the star formation is shifted relative to the galactic plane by around 20 degrees.
Okay.
So in that respect, it's not that unusual. But still, the regions that are this low down, they are pretty isolated. You have some degree of star formation happening there. But to have two dependent populations in the same line of sight, in the same, very close to one another, just a few tens of parsecs apart. That would be kind of odd. For example, there is another region called Taurus.
Yep.
Also shown in this plot.
Mhm.
So these buttons, the only thing they change are the proper motions.
Mhm.
So those lines, those vectors, they show how the stars are moving over time, and we can change the reference frame just to see
Oh,
how
wow.
one region is moving relative to one another.
Got
So
it.
it's a bit busy, but
I'm with you. I got it.
so Taurus is located a few hundred parsecs away. Well, around 100 parsecs away from Perseus. To have two different populations within the space that is smaller than individual star-forming regions like Orion, that is surprising. Along the galactic plane, you might expect it because along the galactic plane, you have a lot of gas. There are some very busy regions like in Cepheus or in Vela, but in Perseus, that is a bit unexpected. And so by trying to understand how the stars have been moving together and trying to trace them back, how they were moving relative to one another over time, we were trying to figure out, well, why precisely has this happened?
There we go. Mm-hmm.
So if we were to, let's shift everything to the right a bit, just so that we're looking at it. Just drag and hold and rotate it.
Okay, that gives me that one. Oh, there we go. Like that?
No, not quite like this. Let's do let's reset the orientation on the x-axis.
Okay.
And let's try rotating it so that we're looking at the xz axis rather than yz axis.
Okay.
Maybe you see the row of buttons at the top. Click on Z. Yeah.
Ah, there we go.
Mm-hmm.
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 Yeah, like this?
Yes.
There we go. Mm-hmm.
And so the morphology of the cloud here is kind of interesting looking because it continues on straight and then it flattens out.
Yes. Mm-hmm.
And it seems to be flattening out perpendicularly to the group that is sitting behind it.
Yes. Okay. Mm-hmm.
And this, I mean, it could happen naturally, but it's also possible that originally the cloud was straight, but something has pushed on it.
Yes.
Flattened it out.
Mm-hmm.
And you see that this group that is sitting behind it is actually expanding. So you have IC348 and you have all the other stuff in the area. So it is possible, IC348 actually has a rather peculiar velocities because it is obviously coming from the group that is in the back, what we refer to as per OB2A.
Okay.
But on the other hand, actually, if you click on all of Perseus, you can see how by subtracting a different component of proper motions,
yes.
we can change the perspective of how we're looking at this region. IC348 has inherited the velocities of the per OB2B as well, so the groups that
Okay, good.
So there has been some degree of interaction. What kind of interaction? There are few various possibilities. So first of all, there probably have been a supernova in this region. There is actually one runaway star that is very, very massive. It's singularly most massive star in the cluster. Normally, they produce a runaway that is the most massive star, unless there was another star that has been more massive. That star probably has exploded, and it has created this runaway. So there has been a supernova in this region, and that supernova could have pushed on the gas as well to create this bend in the cloud.
Yeah, okay.
And if you imagine that this cloud was originally straight without this bend, it would have connected to IC348.
Okay. Yep, perfect.
So you have the velocity of one cloud, you have the velocity of another cloud, and you have this cluster that is stuck in the middle.
Yep. Where'd it go?
It's possible that some time ago, these two clouds have collided to produce this cloud cluster.
Correct. Right.
So that could be one of the explanation for why it is kind of stuck in the middle. Alternatively,
Cool. Okay.
people don't necessarily like it when I go into it because it confuses them. But you have to think about the gravity of it all. The cloud itself is a fairly massive entity. And it stands to reason that it is possible that this cloud exhibits the potential. I mean, because the cloud would have to exhibit the potential on the other stars around it. Young stars, they have fairly low velocities.
Okay.
So it doesn't really take much to alter the trajectory in a noticeable way. For the field stars, you wouldn't see it because they are already moving too fast. If you shift the trajectory a little bit, they will just still continue moving very fast. But in the young stars, you do notice it.
Okay.
The IC348 is located fairly close to the cloud.
Yep.
It is also possible that it is just following the potential in the region, moving towards the cloud as well. So that could be another reason why IC348 is affected by the kinematics per OB2B. So, yeah.
Right.
Okay. This another thing that is worth noting is Cineris and Alcaeus are located on two opposite parts of this region. So the Alcaeus is located in per OB2B, and Cineris is located in per OB2A.
Okay.
Them being the oldest populations, they already have the distinct velocities of two different populations.
Okay.
That is to say, whatever velocity gradient that has formed in this region couldn't have been triggered. That is to say, for example, if you imagine a supernova pushes on the gas, that gas starts forming stars. The new stars will have different velocities from the older stars.
Yes.
But that's not quite what we see here. We see that there are these two different populations already present, starting from the oldest ages. So this effect really is coming from two different populations. It's not that this particular velocity structure has been triggered in this region.
Fair enough. Okay.
But the per OB2A is expanding. I mean, we've seen before that it traces back to the same point, but it is visibly kind of has a spherical expansion. And it could be because of a supernova. The supernova just loses energy, the region becomes unbound, or it could be that this region is not really all that massive to begin with.
Okay.
And everything is naturally starting to disperse and over time. Yeah.
Very cool.
Now, I do have Taurus in this region as well. Shown because it's also a nearby cloud, nearby surrounding region that also has very young stars with an ages of only around 2 million years. And recently there was a paper that would suggest that there is a bubble between Taurus and Perseus.
Okay.
Because when you look at it in the plane of the sky, just the way that different clouds are oriented relative to one another, it looks like there's a dust bubble.
Okay.
And so people have been going back and forth a bit on it a bit because we recognize that Taurus and Perseus are found at two different distances. But this paper have tried to analyze the three-dimensional dust structure, and they if you squint a bit, you might be able to see these two clouds connect to one another. Except,
Sure.
well, you may look at it in the dust. You can also look at it in the stars. And tracing back all the stars, they don't really expand from a central point.
Okay.
So if you have some sort of a bubble, well, that bubble isn't really expanding. So is it really a bubble, or it's just an some peculiar structure in the dust distribution?
Okay.
And also, if you were to, for example, create a supernova to form a bubble, well, what would that supernova come from? You need to have a very massive star. That star can't come from Perseus, it can't come from Taurus because they are both too young.
Yeah.
Also, Taurus is fairly diffuse, so Taurus doesn't form any OB stars. I think the most massive star that you have on Taurus would live for another 100 million years.
Okay. Okay.
And there isn't really anything in between Taurus and Perseus. There aren't really any other star-forming regions. There aren't really, well, there could be a stray OB star that just happened to have passing through, but barring something like that, it doesn't seem very likely that there has been a supernova that could have formed a bubble between these two regions.
Okay, that's curious. All right.
And also, well, to the side, there's California cloud.
Yes, which we've been avoiding.
Yes. Because California isn't really considered to be part of per OB2 because you can see it's pretty much much further away.
Much farther away.
The reason why I've included it in this analysis is not only that it's located in the vicinity of Perseus, but also if you look at kinematics of California, it has very similar kinematics to per OB2b, not to per OB2a, but to per OB2b.
Okay.
Now it could be just a big coincidence. It could be also part of some sort of a larger scale structure.
Yeah. Okay.
But it is still curious that they have such similar kinematics in the plane of the sky, at least. In radial component, they are a bit different. California, if you look, see the line, the dashed line is this is their current position. The dashed line shows how they were moving.
Yep.
So California is coming towards Perseus. Maybe eventually they might be able to, well, they will get closer together. They might be able to, well, I don't know if merge will be the correct word or not.
Interact.
Yeah, they would interact to some degree. But it's still, it could be because of some sort of a potential because again, the Perseus itself is fairly massive. It may be that California is infalling towards it, or it could be part of some sort of other kinematical structure in this region.
Okay,
but
that is curious.
But California cloud is kind of interesting because normally when you think of a cloud in astronomy, you tend to think of a filament.
Yeah.
Because if you, for example, if you have a cloud, it will quickly form a sheet, collapsing along one axis, and it will rapidly collapse along the other axis to form a filament. And from that filament, you're going to start forming stars.
Okay.
California isn't quite like a filament. It is more like a sheet.
Okay.
If you scroll down to the next figure.
Sure. Figure 6. California. Okay.
Yeah. So looking at the bottom left panel,
Mhm.
This is showing the distribution of parallaxes of the stars in California.
Okay.
And so the data are shown in blue. The red histogram shows the expected distribution of parallaxes if all the stars were actually found on the same distance,
Yes.
scattered by the uncertainties.
Mhm.
So the data have a much larger distribution of parallaxes than if everything was found at the same distance.
Right.
And recently there was another paper suggesting that the California cloud is actually a sheet that is something like 120 parsecs long, maybe longer.
Okay.
So this distribution of distances is consistent with it being a very, very long sheet.
Okay.
And the top left panel shows how it looks like in the plane of the sky. So it does kind of look like a filament, but you also have the distance components that would make it into a sheet.
Right. Right. Push it into the plane.
Yep. Yep. And the panel right next to it shows the distribution of polar motions of the stars in California, and it also shows the distribution of parallaxes, with the red being the stars that are more distant. The blue shows that the stars are closer in.
Okay.
That core group that is like more distant, that you can see in red, it kind of near the center of the filament. If you look at the left panel to it, we also have age estimates of the individual stars, not just of the group as a whole, but the individual stars. You can see that this group is actually the youngest group in this region.
Right.
So it's very deeply embedded, and it's kind of sitting behind all of the other cloud, and it has very distinct motion as well.
Okay.
And on the bottom right panel, here we're comparing the various velocity components as a function of parallax, and you can see that there might be some sort of gradients in all of the velocity components throughout the cloud. So the cloud isn't collapsing. It isn't going to form a filament by the looks of it. Rather, if these gradients are to be believed, it's continuously being stretched out. So the stars that are more distant, they're lagging behind the stars that are closer towards us.
Okay. Very good. Okay.
So I think that's basically it for the discussion of the paper. I think we've addressed most of it. This region is interesting and it's very peculiar, and hopefully eventually we'll be able to understand this region and regions like it a bit better.
Well, we're going to come back to that topic here in a minute. So very cool. Very, very nice. Well, thank you, Marina, for walking us through your AJ article. Very nice. And now we'll come back to that future forward. So kind of where do we go? Let's say over the next couple of years. Are there additional maybe multi-wavelength observations of this region? Maybe JWST can do something, or maybe Rubin can do something. Are there other systems where you've got potentially interacting clouds going on that can help inform what's going on in this one? So just sort of where do we go over the next couple of years?
Yeah, absolutely. So Perseus is just one of dozens, if not hundreds, of star-forming regions we have nearby us that we can dig into a similar level of details. With Gaia, we have been able to evolve these regions back in time to understand what is happening to them, how everything is moving. And right now, our understanding of them is still fairly serendipitous, that we knows this particular region. We can try to figure out how this particular region has been evolving, but it's hard to make general statements from that still.
Okay.
So we know that the dominant dynamics in this region, we don't know the dynamics of this region. We don't have a broad overview of their dynamical process in detail. So right now we're still kind of cherry picking some of the regions.
Okay.
And for the most part, we're sticking to some of the regions that have been most well studied.
Right.
In part because in order to understand their dynamics, you need to have access to all of the components of their velocities.
Mm-hmm.
With Gaia, we have proper motions. That is great. Proper motions are not enough. We need to have three-dimensional motions.
Right.
We need to be able to make these three, just like we were playing around with the interactive plot. We need to be able to do it in 3D, because without knowing the radial motion, we're missing half of it.
Right.
And radial velocities are still hard to come by for young stars. To have a radial velocity, someone needed to take a spectra of the star, and you wouldn't take a spectrum of a star just randomly. Someone needed to target it specifically.
Right.
Until recently, we just focused on some of these well-studied surrounding regions, such as Perseus, Taurus, Orion, Scope-Sen, the regions where we have the most detailed understanding of the kinematics. With Gaia, we're discovering hundreds of these regions that we have no idea what they were before.
Potential.
Yeah, so there are some large-scale radial velocity surveys that are coming online. One of them is SGSS5.
Yes.
There are some on the European side of things as well.
Mm-hmm.
And with these radial velocity surveys, now they are aware that the young stars are interesting and that they're worth pursuing. They're found outside of just these few select regions. So there are a few large programs that are aiming to get radial velocities of all of these stars.
Very cool.
And of course, with radial velocity, you also have other fun stuff, such as various lines, such as lithium. Lithium is very important for young stars. You can have H alpha. You can have all sorts of other interesting interesting tracers of their use as well.
Yeah.
You can get temperatures and surface gravities. Surface gravities are also, because these young stars, they're still puffy. They by looking at the surface gravity, you can actually get their ages.
Yeah.
So with these spectra, we'll be able to understand these stars and the regions in which they're found much better than we can right now, just with plain old sky information.
Cool. Well, this is going to be a very exciting topic over the next couple of years as we start expanding this out. Particularly these radial velocity surveys will be huge. So really, yes. Very nice. Marina, I want to thank you once again for walking us through your very lovely article and pointing us toward the future. Very nice.
Well, thank you for having me.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.